Good day, students! How are you doing? This is me again, Sir Navarro, and welcome to our YouTube channel. So for today, we're going to discuss about quadratic functions, alright? So, quadratic functions. So before we discuss the terms, the definition of quadratic function, let's consider a rectangle whose width is x plus 2 centimeter and whose length is x plus 5 centimeter. X here is a positive integer, right? Since we are talking about measurements, okay? So the question is, how do you find the area of this rectangle? So proceed. So given the problem is illustrated as below, right? So see there, the length is x plus 5 and the width is x plus 2, alright? So recall the formula for the area of a rectangle. If you still remember, area of a rectangle is length times width, right? So considering the area of the rectangle, the length times width, we now replace these values with whatever the value of the length and the width is. So x plus 5 and x plus 2, right? So now, if we multiply this 2, we get centimeter times centimeter, that's square centimeter, right? And then if you still remember FOIL method, okay, so x plus 5 times x plus 2 is, then you do the FOIL method, you get x squared first, and then 5x plus 2x, then 5 times 2 is 10. So basically that's x squared plus 7x plus 10 square centimeters, alright? So again, x is any positive integer. It could be also 0, but yeah, since we are talking about measurements, alright? So in this section, if we let some values of x, let's say positive 3, right? So if we have it as positive 3, and then we substitute it here in this equation, right? So basically that's x squared, so 3 squared, and 7 times 3 plus 10. The function will get 9 plus 21 plus 10, that's basically 40 square centimeter. So notice that in the given here, the area of the rectangle is represented by a function a, or f of x, right? Which is x squared plus 7x plus 10. And notice also that the degree of the expression here is 2. So this is an example of a quadratic function, right? So this is also an example of the application of quadratic function. So area represented by any like function notation f of x. This can also be represented as the variable y. Mostly f of x, but sometimes f of a, or f of x, or y basically, right? So again, the degree is 2, and then you have this notation, alright? So let's proceed. So the following are examples of quadratic function. This one, x squared plus 7, 6x squared minus f of x equal to x squared plus 7, f of x equal to 6x squared minus 4x plus 3. And then here we have your y. So y is the same with f of x. I discussed this one in the video that we had during the functions and relations, alright? So the notations. So y equal to 9 plus 2x minus x squared. Y equal to x squared minus 6x minus 16. And also f of t equal to, the function notation represents whatever the variable that you are using here. So it's just even if you want to use y, or it's up to you, as long as it follows the process. So f of t equals to t times t minus 1 over 2, then y equal to x plus 7 squared minus 9. So why do you think that these examples are called quadratic functions? So again, going back to the definition, quadratic function has a degree of 2, of course, right? And then is represented by a function notation. Okay, and these are not examples of quadratic functions. So why do you think that these are not examples of quadratic function? Because if you notice in the first example, the degree is 1. Second is the degree is what? Oh, it has an exponent, but this time it's a variable. And then in number 3, so it has an exponent, yes, but is it 2? Is it in the degree of 2? No. So it's in the degree of 3. So it's cubic. Okay. 4, if you notice, we have here a radical. Okay, radical. The variable x is enclosed into a radical. And then also we have an exponent which is a variable x. The number 5, if you try to do distributive property on this, multiply it here, it becomes x cubed, right? So it's not a quadratic function. Okay, so what is really a quadratic function? So a quadratic function has a form of y equal to ax squared plus bx plus c, where a must not be equal to 0. So if you notice, this is just a similar definition to the quadratic equation, right? But this time, it's not the equal sign, the number or the expression after the equal sign, it's not 0 anymore. It's something else. It's a notation, right? It represents something. Okay, so basically in this manner, let's move this video. Basically in this section, let's right here. In this section, you have the only thing that that is similar to the definition of the quadratic equation is it has a degree of 2. Okay, but there are also aspects here that pertains to different properties. All right. So for example, in a function we graph it, and then the graph of a quadratic function is U-shaped. All right, and it's called a parabola. Okay, parabola, and yeah. So the lowest, and it has some properties, which is the lowest or the highest point on the graph of a quadratic function it's either this one, lowest, or if you try the orange one, it's the highest. It's what we call the vertex. Okay, and then the graphs of yx squared and y equal to negative x squared are symmetric. So it has a lot of properties called the axis of symmetry. So this one is the axis of symmetry, which is the y-axis. Alright. So these properties will be discussed further on our next video. But this time we're just going to discuss everything focused on how to identify quadratic function given a table. Alright. Because if you're given a graph, of course, it should be in a U-shape so that it can be a function, and also it must pass through the y-axis. All right, so that's a function. But how are you going to identify if it's and then also we're done with if given an equation. All right, but how are you going to identify if the given is not a graph, not an equation? So it's in a table, like particular ordered pairs are given. Okay, so now let's proceed. So now that you know how to identify a quadratic equation given an equation and then given a graph, how will you identify a quadratic function from a given set? Alright, given set of ordered pairs only in a table of values. Okay, so let's consider the ordered pairs of values for the quadratic function f of x squared for the integers like this, -3, then x is less than or equal to positive 3, but greater than or equal to -3. So these are the numbers, the values of x, right? And then these are the ordered pairs. So -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, 9. So I discussed how to make this one as this is an ordered pair, and then I discussed it already how to make this one into table form. So you're just going to, even if there's a repeating value in the y-axis or in the x coordinates or y coordinates, it's okay. You can just put it like this. All right. So just put the pairs. Okay. Anyway, it's arranged already. So yeah, that's okay. So since this is a y, y equal to x square, or the equation is x square, or the function is x square, so basically the square lang sa mga x's, no? So square of negative 3 is 9, and then same with the other side. So square of 0 is 0, of course. So basically, if we try to look into the table, if we try to look into the table values, and then we check the differences in the x. Let's try to see. So let's see the difference in x. So if we take the difference, we subtract the like negative 2 minus 3, that's still 1, right? And then negative 1 minus 2, 1. So 0 minus the negative 1, it becomes 1. 1 minus 0, that's 1. 2 minus 1, that's 1. 3 minus 2, that's 1. And then if we try to see in the second, these are the differences in the x-axis, right? This 1. And then if we try to take the differences in the y value, so 4 minus 9, that's, and then 4 minus 9, that's negative 5. 1 minus 4, that's negative 3. 0 minus 1 is negative 1. 1 minus 0, that's 1. 4 minus 1, that's 3. 9 minus 4 is 5. That's the first. Let's call this difference in y as the first differences in y. Now after that first difference, let's get the second difference, right? So negative 3 minus the negative 5, that's 2. Negative 1 minus the negative 3, is 2, and so on. It becomes 2. So this is the second differences in y. So what have you noticed with the differences in the x values? Right, it's 1, of course. It's 1. What about the differences in y? So in the first difference, they're not the same, right? But in the second difference, they're the same. So that's one thing you have to consider if you are to identify a given table if it's a quadratic function. Because because it's the definition of the quadratic function. So if you're given a table, so you have to take the differences in the y values, and then in the second differences, they should be the same. Okay? So let's have another example. So consider the table of values for the quadratic function. This time it's another function, but if you're not given this function, you're just given this table. So here are the values: negative 3, negative 1, 1, 3, 5, 7, 9. So and then the corresponding values: negative 13, 3, 3, negative 13, negative 45, negative 93, negative 157. So now if we take the differences in the x, okay, so negative 1, or pwede rasa 3, 9 minus 7, that's 2, right? So then we follow, they're all the same. So negative 3, and negative 1 minus the negative 3, that's 2. Same with the others. So let's try to check in the first differences in y. Negative 30, and then 3 minus negative 13, that's positive 16. This one, 0. This one, negative 16. This one, negative 32, negative 48, negative 64. So this is the first difference in y. What about the second difference in y? So let's try to check. The second difference are the same. So 0 minus 16, that's negative 16. Negative 16 minus 0, that's negative 16. Negative 32 minus the negative 16. So that's negative 16 again, and negative 16, negative 16. So the second differences in y are the same. So that means this is a function. So when can you tell that the given table is not a function? If the first difference are the same. Okay, it's a linear. If the first difference are the same, then it's a linear. But if the second difference are not the same, then you still have another differences here, then that is also not a quadratic function. So observe that the like in the f of x squared, the table of values for f of x equal to 5 minus 2x squared show that equal differences in x produce equal differences in y equal to f of x. This is true for all quadratic functions. I think that. Thank you and God bless.